So, welcome. I hope you're all in the right place. Welcome to EECS 498-007/598005. This is special topics class taught for the first time here at Michigan on deep learning for computer vision. I wish we had a snappier, more easy to remember course number, but when you teach a special topics class, they give you numbers like this. So I'm sorry about that. But hopefully you're all in the right place. So before we get started, I wanted to talk a little bit about the waitlist. So I know we had a lot of interest in this class, much more than we could possibly accommodate. So because we only have about 120 slots in the class, and when I checked yesterday, we had something like 135 people on the waitlist. So no matter which way we slice it, unfortunately, many people who will want to take this class just unfortunately won't be able to get in. So I'm really sorry about that. But we will try to get as many people in as we can, and stay tuned. We'll be sending out a couple more overrides later today. And as we move on in the quarter, if anyone drops, I'll definitely be adding in more people. But I apologize in advance if you're not able to get a slot in this class when you wanted to. So with that out of the way, let's get started on the course material. So the title of this class is Deep Learning for Computer Vision. So I think we need to unpack a little bit what these terms mean before we get started. So computer vision is the study of building artificial systems that can process, perceive, and otherwise reason about visual data. And this can have quite a broad definition. What does process, what does perceive, what does reason mean? It's kind of up for interpretation. Or what does visual data mean? That could be images, that could be videos, that could be medical scans, that could be just about any type of continuously valued signal you can think about can sometimes be found in computer vision conferences or publications somewhere. So these terms are really defined quite broadly. So why is computer vision important? Well, I think computer vision is a particularly important and exciting topic to study because it's everywhere. I think many of us in this room right now are carrying around one or more, several cameras, and we're just taking millions of photos every day. There's cameras all around us all the time. People are always creating visual data, sharing visual data, talking about visual data. And it's very important that we build algorithms that can perceive, reason, and process it. For a couple of concrete statistics, if you look at YouTube, actually, no, let's talk about Instagram first. So Instagram is very popular. I think many of you are familiar with it. And there's something like 100 million photos and videos uploaded on Instagram every single day. If we go on YouTube, it's even worse. So on YouTube, as of 2015, so I'm sure it's grown since then, people are uploading roughly 300 hours of video on YouTube every minute. So that means if you do the math and you think, if I wanted to, as a single individual human being, look at all the visual data just being uploaded on Instagram and YouTube in one day, if you do the math, say I'm going to look at images for maybe 1 second each, I'm going to look at my YouTube videos at double speed, it's going to take me about 25 years to look at the visual data that's going to be uploaded on just these two sites in a single day. So when you think about these massive statistics, and think about the massive amount of visual data being processed and shared across the internet these days, it becomes clear that we need to be able to build automated systems that can deal with it, because we just don't have the human manpower to look and process and perceive all of the data that we're creating. So that's why I think computer vision is such an important topic to be studying these days. And it's only going to get more important as the number of visual sensors out in the world keep increasing. With new emerging technologies like autonomous vehicles, augmented and virtual reality, drones, you can imagine that the role of computer vision in our modern society will just continue getting more and more and more important. So clearly I'm biased because this is my research area, but I think this is the most important and exciting research topic that we can be studying right now in computer science. So that's computer vision. Computer vision is the problem that we're trying to solve. It sets forth this problem of understanding visual data, but computer vision doesn't really care how we solve that problem. Our goal is just to crunch through all of those images and videos however we can. But the way that the technique that we happen to be using in computer vision across the field these days is deep learning. So before we get to deep learning, what is learning? Learning is the process of building artificial systems that can learn from data and experiences. Notice that this is somewhat orthogonal to the goals of computer vision. Computer vision just says, we want to understand visual data, we don't care how you do it. Learning is this separate problem of trying to build systems that can adapt to the data that they see and the experiences that they have in the world. And from the outset, it's not immediately clear why these two go together. But it turns out that in the last 10 to 20 years, we found that building learning-based systems is very important for building many kinds of generalizable computer systems, both in computer vision and across many areas of artificial intelligence and computer science more broadly. So now, when we think about deep learning is then yet another subset of machine learning, where deep learning is sort of maybe a bit of a hypey name, a bit of a buzzwordy name, but my definition is that it's a type of deep learning consists of hierarchical learning algorithms with many layers, whatever that means in the context at hand, that are very, very loosely inspired by the architecture of the mammalian brain and sometimes mammalian visual system. Now, note that I say loosely. This is a thing that you'll often see people talk about in deep learning, that it's how the brain learns or how the brain works. I think you should take any of these comparisons with a massive grain of salt. There are some very coarse comparisons between brains and neural networks that we use today, but I think you should not take them too seriously. So then, kind of stepping back a little bit from these two topics, computer vision and machine learning both fall within the purview of the larger research field of artificial intelligence. So artificial intelligence is very general, very broad. It's broadly speaking, how can we build computer systems that can do things that normally people do? So that's kind of my definition. I think people will argue about what is and is not artificial intelligence. But I think we just want to build smart machines, whatever that means to any of us. And I think there's clearly many different subdisciplines of artificial intelligence, but two of the most important, clearly again in my biased opinion, are computer vision, teaching machines to see, and machine learning, teaching machines to learn. And these are the topics that we'll study in this class. So then kind of where does deep learning fall in this regime? Deep learning would be a subset of machine learning, and it intersects both computer vision and falls within the larger AI realm. I think it's important at the outset so then this class is going to focus at kind of this intersection right in the middle, the intersection of computer vision, machine learning, and deep learning. The reason I want to start out with this slide is because it's really easy to get caught up in the hype these days and think that computer vision is the only type of AI, deep learning is the only type of AI, deep learning is the only type of computer vision. But I think none of these are true. There are types of AI which have nothing to do with learning, nothing to do with deep learning. There's classical results about symbolic systems and other approaches to AI that are very different technically. There's areas of computer vision that do not use very much machine learning or very much deep learning. So even though the focus of this class will be the intersection of these different research areas, I just want you to keep in mind as a whole that there is a much broader realm of AI research being done today around the world by different groups that falls into different pieces of this pie chart. And of course, there's many other areas within AI that we won't talk about too much. So there's natural language processing, things like speech recognition, things like robotics, and I kind of ran out of space on the chart to put any more sub-areas. But suffice to say, artificial intelligence is a massively successful, massively popular area of research and area of study these days. That, again, with the broad goal of making machines do things that people normally do, you can imagine that there's a whole lot of things that we might do out in the world that fall under this umbrella of artificial intelligence. So that's kind of the big picture roadmap. And now for the rest of the semester, we're going to focus on this little red area in here. But again, don't forget that there's a lot more to the world than what we're talking about in this class. So today's agenda is a little bit different from most of the lectures in this class because, again, it is the first week. So before we can really dive into that red piece of the pie chart and talk about machine learning and deep learning and computer vision, all that really good stuff, I think it's important to get a little bit of historical context about how we got here as a field. This has been a hugely successful research area in the last 5 to 10 years, but deep learning, machine learning, computer vision, these are areas with decades and decades of research built upon them. And all of the successes we've seen in the last few years have been a result of building upon decades of prior research in these areas. So today I want to give a brief history and overview of some of the historical context that led up to the successes of today. And then following that, we need to talk about some of the boring stuff, the course overview, logistics, all that other stuff that you expect to see in a first lecture in a class. So let's start with, so we're going to do this in two ways, right? We're going to do a parallel stream. First, we're going to talk about the history of computer vision. Then we're going to sort of switch a little bit and cover the history of deep learning. So before we dive into the material, is there any sort of questions before we launch into this historical escapade? No? Okay, perfectly clear. So if we go, I think whenever you talk about a research area, it's always difficult to pinpoint the start, right? Because everything builds on everything else. There's always prior work. Everyone was inspired by something else that came before. But with a finite amount of time to talk about a finite number of things, you've got to cut the line somewhere. So one place where I like to draw the line and point to as maybe the start of computer vision is actually not with computer scientists at all. It's from this seminal study of Hubel and Wiesel back in 1959, who were not interested in computers at all. They wanted to understand how mammalian brains work. So what they did is they got a cat, they got an electrode, they put the electrode into the brain of the cat, into the visual cortex of the cat, which is the part in the back of your head that processes visual data. And with this electrode, they're able to record the neuronal activity of some of the individual neurons in the cat's visual cortex. So then, with this somewhat grotesque experimental setup, they were able to have the cat watch TV. And then, well, not really TV because it was 1959, but they were able to show different sorts of slides to the cat. They could show, they had this general hypothesis that maybe there's certain neurons in the brain that respond to different types of visual stimuli. And by showing the cat different types of visual stimuli and recording the neuronal activity from individual neurons, maybe we can start to puzzle out how this thing called vision works at all. So that's exactly what they did. They got these cats, they stuck neurons in their brains, and they started showing them lots of different images on a slideshow to try to see what kinds of images would activate the neurons in the cat's brains. So they tried different things. You can show them maybe mice and fish and other kinds of things that cats like to eat or play with. But it was really hard to get any solid signal about what these neurons were responding to. So what one really interesting discovery happened is, today we're using PowerPoint, but back in the day we had actual slide projectors. And when you change the slide, like there was kind of a vertical bar that would move up and down the screen. And what they surprisingly found is that some of the neurons in the cat's brain would consistently respond to the time when they changed the slides. And even though they couldn't recognize any patterns of how was the cat responding to things on the slides. And they eventually discovered that it was in fact this moving vertical bar that was indeed causing some of the neuronal activity in the cat's brain. So with this hint, they were able to puzzle out that there are different types of cells in the brain that are responding to different types of visual stimuli. Many of them are very hard to interpret, but some of these easiest are these so-called simple cells that they discovered. So the simple cells would respond to an edge that's maybe light on one side, dark on another side, at a particular orientation, at a particular position in the cat's visual field. And if there happened to be an edge at the right position and the right angle and the right place, then that particular neuron might fire. That was very exciting because then they had some concrete evidence of what it is that cats are actually responding to in their brains. Then with a bit more exploration, they were able to find other types of cells in the brain that responded to even more complex patterns, like the complex cells that would respond to bits of motion or could respond to oriented edges but anywhere in the visual field to give some sense of translation and variance in the visual representations that they perceive. So I think that this is really one of the foundations. Oh, and by the way, of course, I have to mention that this was very seminal research, and these guys won the Nobel Prize for it in 1981. So this was very important research in history of science and psychology and vision overall. But I like to point to this as the beginning of computer vision for a couple reasons. One is this emphasis on oriented edges. We'll see this come up over and over again on the different architectures that we studied throughout the semester. The other is this hierarchical representation of the visual system, of building from simple cells that represent one thing, combining with complex cells and more complex cells that respond to more and more complex types of visual stimuli. This broad idea was hugely influential on the way that people thought about visual processing and even on neural representations more generally. So then, if we move forward a couple years to 1963, Larry Roberts that's when Larry Roberts graduated from MIT with his PhD and did perhaps what was the first PhD thesis on computer vision. Here, of course, it was 1963. Doing anything with computers was very cumbersome. Doing anything with digital cameras was very cumbersome. So large portions of his thesis just talk about how do you actually get photographic information into the computer, because this was not something you could take for granted at that time. But even working through those constraints, he built some system that was able to take this raw visual picture, detect some of the edges in the picture, sort of inspired by Hubel and Wiesel's discovery that edges were fundamental to visual processing. Then from there, detect feature points, and then from there, start to understand the 3D geometry of objects and images. Now, what's really interesting is that if you go and look at Larry Roberts' Wikipedia page, it actually doesn't mention any of this at all, because after he finished his PhD, he went on to become the founding father of the internet, and went on to be a major player in the World Wide Web and all of the networking technologies that were developed around that time. So doing the first PhD thesis in computer vision was kind of a low point in his career. I think all of us can aspire to be that successful. So then, moving forward a couple more years, people were getting really excited. So there was this very famous study in 1966 from MIT. Seymour Papworth proposed the Summer Computer Vision Project. The Summer Computer Vision Project, basically what he wanted to do is like, okay, we've got digital cameras now, we can detect edges, we know how Hubel and Wiesel told us how the brain works. What we're going to do is hire a couple undergrads, put them to work over the summer, and after the summer, we should be able to construct a significant portion of the visual system. Man, these guys are really ambitious back in the day. Because now it's clearly computer vision is not solved. They did not achieve this lofty goal. And nearly 50 years later, we're still plugging away trying to achieve what they thought they could do in the summer with 5 undergrads. So moving forward into the 1970s, one hugely influential figure in this era was David Marr, who proposed this idea of stages of visual representation that again kind of harkens back to Hubel and Wiesel. So here you can see that maybe we want the input image, then we have another stage of visual processing where we extract edges, then from the edges we extract some kind of depth information that maybe we can segment objects and say which parts of the image belong to different types of objects. And then think about the relative depths of those objects. And then eventually start to reason about whole 3D models of the world and of the scene. And then moving forward in the 70s, people were started to become interested in recognizing objects and thinking about ways to build computer systems that could not just detect edges and simple geometric shapes, but more complex objects like people. So there was work about some things like generalized cylinders and pictorial structures that tried to recognize people as these deformable configurations of rigid parts with some kind of known topology. And you can see ideas, and this was very influential work at the time. But the problem is that in the 1970s, processing power was very limited. Digital cameras were very limited. So a lot of this stuff was sort of toy in a sense. And as we move into the 80s, people had much more access to better digital cameras, more and more computational power, and people began to work on slightly more realistic images. So one kind of theme in the 80s was trying to recognize objects and images via edge detection. I told you that edges were going to be super influential throughout the history of computer vision. So there was a very famous paper from John Canny in 1986 that proposed a very robust algorithm for detecting edges in images. And then David Lowe, the next year in 1987, proposed some mechanism for recognizing objects in images by matching their edges. So in this example, you can imagine we've got this cluster of razors, and then we detect the edges. Then maybe we have some template picture of a razor that we know about. Then we can detect the edges of our template razor and try to match it into this image, this cluttered image of all the razors. And then by kind of matching edges in this way, we might be able to recognize that there are maybe 10 razors in this image and what are their relative configurations, just based on matching with our template image. And now moving on into the 1990s, people again wanted to build to more and more complex images, more and more complex scenes. So here a big theme was trying to recognize objects via grouping. So here, rather than maybe just matching via edges, what we want to do is take the input image and segment it into semantically meaningful chunks. Maybe we know that the person is composed of one meaningful chunk, the different umbrellas would be composed of a different meaningful chunk, with the idea that if we can first do some sort of grouping, then later downstream recognizing or giving a label to those groups might be an easier problem. Then in the 2000s, a big theme was recognition via matching. And there was a hugely famous paper called SIFT by David Lowe again in 1999 that proposed a different way of recognition via matching. So here the idea is that we would take our input image, detect little recognizable key points in different 2D positions in the image, And at each of those key points, we're going to represent its appearance using some kind of feature vector. And that feature vector is going to be a real valued vector that somehow encodes the appearance of the image at that little point in space. And by very careful design of exactly how that feature vector is computed, you can encode different types of invariances into that feature vector, such that if we were to take the same image and rotate it a little bit, or brighten or darken the lighting conditions in the scene a little bit, that hopefully we would compute the same value for that feature vector, even if the underlying image were to change a little bit. And there was a lot of work in so then once we can extract these sets of robust and invariant feature vectors, then you can, again, perform some kind of recognition via matching. So then on the left, if we have some template image of a stop sign, we can detect all these distinctive invariant feature key points. Then on the right, if we have another image of a stop sign that's maybe taken from a different angle with different lighting conditions, then by our careful, clever design of these invariant, robust features, then we can match and correspond points in the one image into points in the other image, and thereby be able to recognize that the right image is indeed a stop sign. So then another hugely influential work in the 2000s was the Viola-Jones algorithm, published in 2001. And this was really, and they developed a very, very powerful algorithm for recognizing faces in images. So here they would, you have an image and then you want to draw a box around where all the people's faces are. And this was notable for, this piece of work was notable for a couple reasons. One, it was the first major use of machine learning in computer vision. So Viola and Jones used some algorithm called boosted decision trees that were able to learn somehow the right combination of features to use in order to recognize images, in order to recognize faces. And two, what was particularly notable was the very fast commercialization of this algorithm. That this piece of research went very quickly from a sort of academic piece of research published in 2001, and within a few years, this was actually being shipped in digital cameras at the time. So if you remember, maybe they had like an autofocus feature where you would kind of hold the shutter half down, it would like beep a little bit and draw boxes around the faces and then focus on the people in the scene. Well, that was most likely using this Viola-Jones algorithm. So this is a particularly notable piece of work for those two reasons. So now, after they kind of unlocked the box of using data and using machine learning to augment our visual representations, then moving on into the 2000s, we began to see more and more uses of machine learning, more and more uses of data in order to improve our visual recognition systems. So one hugely influential piece of work here was the Pascal Visual Object Challenge. So here, they downloaded a bunch of, because now it's 2000, Larry Roberts had exited computer vision and invented the internet. So we could then download images from the internet to help build these data sets of images, and then we could get graduate students to go and label those images. And then you could use your machine learning algorithms to mimic the labels that the graduate students had written down on the images. And then if you do that, then you can see this nice graph on the right of performance increasing on this recognition challenge increased steadily over time from about 2005 to 2011. So then this brings us to the ImageNet large-scale visual recognition challenge. So here, this was a very, very large-scale data set in computer vision that has become hugely influential and has become one of the main benchmarks in computer vision, even leading up to this day. So the ImageNet classification challenge was this fairly large data set of more than about 1.4 million images, and each of those 1.4 million images were labeled with one of 1,000 different category labels. And the big new piece of innovation here was that if you're going to do the math here, you're going to need a lot of graduate students to label all this stuff. So the big piece of innovation here was to not label data using graduate students. Instead, this made use of crowdsourcing. So here, you could go on services like Amazon Mechanical Turk and then parcel up little pieces of work and then just blast them out on over the internet. And then people anywhere in the world could label a couple images, get paid a couple cents for each image they label, and that was able to massively increase the amount of I mean, this is beneficial in two ways, right? Because one, researchers get people to label their data without being constrained by the number of graduate students that they have. And two, it became a nice source of income for some people who were bored at work and just like label images a little bit here. Or bored in class, as the case may be. I don't know. It's still running, by the way. You can go up and try to do some tasks now. But anyway, this became a hugely influential data set for computer vision. And more than a data set, it became a benchmark challenge. So they had, every year, they ran a competition where different researchers would compete and try to build their own algorithms that would try to recognize objects in this classification challenge. And this became somewhat jokingly known sometimes as the Olympics of computer vision. That there was a period of time from maybe in the early 2010s, the late 2000s, early 2010s, when people would just really excitedly want to look at the results of the ImageNet competition every year and see what kind of advances the field had made in the last year. So then, given that I told you it's this competition, you can look at what was the error rate on this competition moving over time. So the first time the competition was ran in 2010 and 2011, we were sitting at error rates of around 28, around 25. And then something big happened in 2012. So at the 2012 ImageNet competition, suddenly the error rates dropped in a single year from 25% all the way down to 16%. And after 2012, error rates just kept on diminishing very, very fast. Such that once we got to about 2017, we were building systems that could compete on this ImageNet challenge and perform even better than humans when they try to recognize images in this data set. So then the question is what happened in 2012? So what happened in 2012 is that deep learning came onto the scene. And this was really the breakthrough moment for deep learning. And computer vision researchers suddenly woke up and saw that there's this crazy new thing that is suddenly sweeping our field. So in 2012, there was this absolutely seminal paper from Alex Krzyczewski, Ilya Sutskever, and Jeff Hinton, where they proposed a deep convolutional neural network called AlexNet that just crushed everyone else at the ImageNet competition that year. And for people working in computer vision at that time, this was shocking. This felt like there was this brand new thing that just came out of nowhere and just suddenly crushed all of these algorithms that we've been working on. You know, as we kind of walked through this history of computer vision, walking from the 1950s all the way up until the 2000s, you'll notice that neural networks were not a mainstream part of that history throughout much of computer vision's history. So when this suddenly appeared, it felt to a lot of computer vision researchers like this was this brand new thing suddenly appearing all at once. That's this brand new exciting technology. And that was a little bit flawed because this was not a brand new technology. There had been a parallel stream of researchers going back similar amounts of time that had been developing and honing these techniques for decades. And 2012 was the sudden breakthrough moment where all of that hard work paid off and became mainstream. So then let's talk a little bit about the history of deep learning, kind of going back in time yet again. So then, about the same time that Hubel and Wiesel were doing some of their seminal work on visual recognition in cats, there was another very influential algorithm called actually it wasn't even an algorithm at all, called the perceptron. So the perceptron was one of the earliest systems that could learn as a computer system. But what's interesting is that this was, 1958? So the idea of an algorithm, the idea of programming a computer, these were quite novel research topics on their own at that period in time. So the perceptron was actually implemented as a piece of hardware. Here's a picture of it on the right. That is the perceptron. It was this giant, like, cabinet-sized thing with like wires going all over the place. It had weights that were stored in these potentiometers, which I don't even know what that is because I'm a computer scientist. And these weights were just mechanically the values of these weights were changed mechanically during learning by a set of electric motors, which again, I'm not a mechanical engineer, so I definitely could not build this thing. But even though this was this mechanical device that was bigger than a person, it actually could learn from data somehow. And it was able to learn to recognize letters of the alphabet on these tiny 20 by 20 images that were super state-of-the-art in 1958. So if I didn't put any of them, I don't want to talk about any of the math for the perceptron, but if you were to look at it with modern eyes, we would probably call it a linear classifier that we'll talk about next week on Wednesday's lecture. So this perceptron got a lot of people really excited. It got people thinking like, wow, here's a mechanism that allows machines to learn novel stuff from data without people having to explicitly program how it's going to work. And all of that kind of came to a crashing halt in 1969 when Marvin Minsky and Seymour Papert published this infamous book called Perceptrons in 1969. And what Minsky and Papert pointed out in their book basically was that perceptrons are not magical devices, right? The perceptron is a particular learning algorithm, and there's certain types of functions that it can learn to represent, and other types of functions that it cannot learn to represent. In particular, they pointed out that the XOR function is not something that is learnable by the linear perceptron learning algorithm that we'll talk about again a little bit more next week. And this sudden realization, well, okay, so the normal story that gets told is that the sudden realization of this book was that, oh, these learning algorithms are not magical, there's things they can't learn, and people just lost interest in the field. And work in learning, work in perceptrons, kind of dried up for a period of time following the release of this book. But what's interesting is that I think nobody actually read the book, because if you actually read it, there's sections where they say, yes, the original perceptron learning algorithm is quite limited, and it can only represent certain functions. But there's something else. There's another potential version of the algorithm called a multi-layer perceptron that actually can learn to represent many different types of functions, and it's very flexible in its representations. But that kind of got lost in the headlines at the time, and nobody realized that, and people just heard that perceptrons didn't work and were dead, and people stopped working on them. So you should definitely read the assigned reading. But then, going forward quite some amount of time, we skip ahead to 1980, and there was this very influential paper called, system proposed called the neocognitron that was developed by Fukushima, who's a Japanese computer scientist. And he was directly inspired by Hubel and Wiesel's idea of this hierarchical processing of neurons. Remember, Hubel and Wiesel talk about these simple cells, these complex cells, these hierarchies of neurons that could gradually learn to see more and more complex visual stimuli in the image. So Fukushima proposed this computational realization of Hubel and Wiesel's formulation that he called the neocognitron. So the neocognitron interleaved two types of operations. One were these computational simple cells that, if we were to look at them with modern terminology, they look very much like convolution. And the latter was these computational realizations of complex cells that, again, under modern terminology, look very much like the pooling operations that we use in modern convolutional neural networks. So what's striking is that even back in this neocognitron from 1980, had an overall architecture, an overall method of processing that looked very similar to this famous AlexNet system that swept in 2012. Even the figures that they have in the papers look pretty similar, so they gotta be the same thing, right? But what was striking about the neocognitron is that they defined this computational model. They had the right idea of convolution and pooling and hierarchy, but they did not have any practical method to train the algorithm. Because remember, there's a lot of learnable weights in this system, a lot of connections between all the neurons inside that need to be set somehow. And Fukushima did not have an efficient algorithm for learning to properly set all of the free weight parameters in the system based on data. So then a couple of years later, there was this, again, massively influential paper by Rumelhart, Hinton, and Williams in 1986 that introduced the backpropagation algorithm for training these multi-layer perceptrons. So remember that in the perceptrons book, there was this thing called a multi-layer perceptron that was thought to be very powerful in its ability to represent and learn different types of functions. Well, in the backpropagation, in this paper that introduced the backpropagation algorithm, was one of the first times that people were able to successfully and efficiently train these deeper models with multiple layers of computation. And this looks very much like a modern neural network that we're using today. That if you kind of look at this paper and open it up and read through it, you'll see they talk about gradients and they talk about Jacobians and Hessians and all this kind of mathematical terminology that we think about today when we're building and training neural networks. So these look very much like the modern fully connected networks that we still use today, that are sometimes called multi-layer perceptrons in homage to this long history. So now that led to a lot of people, that led to a lot of small people started to get really excited about neural networks again, and try to think about different types and structures of neural networks that could be built and trained, powered by this new backpropagation algorithm. And one of the most influential works around that time was Jan LeCun et al.'s paper in 1998 that introduced the idea of a convolutional neural network. So this looks, again, very much like the Fukushima algorithm that we saw. Well, basically what they did here is they took Fukushima's kind of idea of convolution and pooling and multiple layers inspired by the visual system, and combined that with the backpropagation algorithm from Rumelhart's paper in 1986. And with that combination, they were able to train these fairly large, at the time, convolutional neural networks that could learn to recognize different types of things in images. And this was a hugely successful system. It actually was very successful commercially. So in addition to being a piece of very influential academic research, it was also deployed in a commercial system by NEC labs. And for a period of time, this convolutional neural net system developed by that group was actually being used to process the handwriting in a lot of checks that were written in the United States at that time. One figure that I found stated that up to 10% of all checks in the United States were actually having the numbers on the check being read automatically by these convolutional neural net systems in the late 90s and early 2000s. And again, if you look at exactly what this algorithm is doing, Linnet was kind of like so the algorithm here was called Linnet after Jan LeCun. I don't know, he's French. And then if you look at the structure of that algorithm, it looks very similar, almost identical to the algorithm that was used in AlexNet nearly 30 years later. So then, emboldened by this success, there was, again, a small group of people throughout the late 90s and early 2000s who were really interested in trying to in push neural net systems and figure out ways to train neural net systems that were ever bigger, ever deeper, ever wider, and could be used on an increasing variety of tasks. And around this period of time in the 2000s was where the term deep learning first emerged, where the term deep was meant to refer to multiple layers in these neural network type algorithms. So this was really not a super mainstream research area at this time. There was a relatively small number of research groups and a relatively small number of people studying these ideas around this time. But I think a lot of the fundamentals that we're reaping the rewards of now were really developed during this period of time in the 2000s, when people started figuring out all the new modern tricks to train different types of neural network systems. So that finally brings us back to AlexNet. And then in 2012, we had this great confluence of this great this computer vision task called ImageNet that people in computer vision were super excited about. We had this set of new techniques, convolutional neural networks, and efficient ways to train them that have been developed by this parallel research community. And everything just seemed to come together just at the right time in 2012. So then from 2012 to present day, we've seen an absolute explosion in the usage of convolutional and other types of neural networks both across computer vision and across other types of related areas in AI and across computer science. So here on the left, we have the Google Trends for deep learning. So that shows you this massive sort of exponential growth that really took off starting in 2012. And on the right, this is a photo I took at the Computer Vision and Pattern Recognition Conference this summer in 2019. So this is one of the premier venues for academic publications in computer vision. And here is a graph that they were showing at the keynote for that conference, where they showed on the x-axis the year of the conference, and on the y-axis is the number of submitted and accepted papers in this conference. So you can see that even though the last 5 to 10 years have resulted in this massive explosion, both of machine learning systems, both maybe in popular perception as measured by Google Trends, as well as a massive increase in academic interest into both machine learning systems and computer vision systems, as evidenced by this plot on the right. And if you look around the field today, we see that convolutional networks and other types of deep neural networks are being used for just about every possible application of computer vision that you can imagine. So from 2012, these convolutional networks are really everywhere. They're getting used from such a wide diversity of tasks, like image classification, where we want to put labels on images, from image retrieval, where we want to retrieve images from collections, things like object detection, where we want to recognize the positions of objects in images while simultaneously labeling them. The right one should be image segmentation. I need to fix the slide. Where we want to label where this is going back to this idea of semantic grouping we saw from computer vision in the 90s, where we want to label the types of pixels as being part of a cohesive whole. ConvNets are getting used for things like video classification, activity recognition. They're getting used for things like pose estimation, where we want to say how are the exact geometric poses of people arranged in images. Even for things that don't really feel like classical computer vision, like playing Atari games, where they would process the visual input of the Atari game with a convolutional neural network and combine that with other sorts of learning techniques in order to both jointly learn a visual representation of the video game world, as well as how to play in that world. Convolutional neural networks are also getting used for visual tasks that are about visual data that humans aren't very good at. So convolutional networks are getting used in things like medical imaging to diagnose different types of tumors, to diagnose different types of skin lesions and other medical conditions. They're getting used in galaxy classification. They're getting used in tons of scientific applications, like classifying whales or elephants or other types of, because there's this problem where scientists want to go out into the world and collect a lot of data and then be able to use images and visual recognition as a kind of universal sensor to make use of all this data that they collect and gain insights into their particular field of expertise that they're interested in. And we've seen computer vision and convolutional networks branch out into all these other areas of science and just open up and unlock lots of new applications just across the board. ComNets are getting used for all kinds of fun tasks like image captioning. Like we can build systems that can write natural language descriptions about images. These are using convolutional networks. We can use convolutional networks for generating art. So we can make all these kind of psychedelic portraits, again, using convolutional neural networks. So then we might ask, what was it that happened in 2012 that made all of this take off? Well, I think the jury's out, and we'll have to see what the historians write 50 years from now. But my personal interpretation is that it was a combination of three big components that came together all at once. One was the set of algorithms, that we saw that there was a stream of people working on deep learning and neural networks and machine learning who had developed these powerful set of tools for representing learnable functions and for learning them with the backpropagation algorithm. We saw the second stream of data, that with the rise of digital cameras, Larry Roberts inventing the internet, and people developing crowdsourcing, we were able to collect unprecedented amounts of labeled data that could be used to train these systems. And the third piece that we haven't really talked about was the massive rise in computational resources that has been continually happening throughout the history of computer science. So one graph that I put together that I find particularly striking is looking at the gigaflops of computation per dollar as a function of time. So here on the blue, you can see these are different types of CPUs. Right? A CPU is central processing unit. It's the thing that's making all of your laptops run. And they get faster, but not that much faster over time. But starting in 2008, there was some really interesting development with GPUs, graphics processing units. So these were these special purpose pieces of hardware that were originally developed to pump out pixels in computer graphics applications. But around 2008, people started developing techniques to run generalized programs on these graphics processing units. And and then over time, these techniques became more and more easy to write general purpose scientific code and mathematical code to run on these massively parallel graphics processing units. And then if you look at the timeline from 2006 to 2017 and look at the gigaflops per dollar of these graphics processing units, you can see that although this exponential Moore's law may not have held up for CPUs, it actually has been, we actually have seen exponential increases in GPU computing power over time, over the last 10 years. And if you look at maybe the and this has been striking even in the last couple of years. So if you look at the AlexNet system in 2012, he was using this GTX 580 GPU that was very, very exciting at the time if you were a gamer. And if you push it on to more recent cards like the GTX 1080 Ti or more recently a 2080 Ti, I've got to update the slides, then you can see that the cards we have even 5 years later are literally exponentially more powerful than the cards that we were using even in 2012. So I think that it was really this confluence of algorithms, of data, and of massive increases in computation fueled by advances in GPUs that led to all this magic happening in 2012, that led to all these new applications of convolutional networks on different types of computer vision. And in recognition of all of this, in recognition of the impact of computer vision and deep learning across the field, the 2018 Turing Award was awarded to Yoshua Bengio, Jeff Hinton, and Jan LeCun for their work on pioneering many of the deep learning ideas that we'll learn throughout this class. And for those of you who don't know, the Turing Award is basically considered the Nobel Prize equivalent in the field of computer science. So this just happened last year, and this was just a recognition that this has been a massively influential piece of research that's been changing all of our lives over the last several years. But I think it's important to stay humble and realize that despite all of the successes that we've seen in convolutional networks, in deep learning and computer vision, I think we're really still a long way away from building systems that can perceive and understand visual data to the same fidelity and power and strength as humans can. One image that I like to use to exemplify this is this example. So if we were to send this to a convolutional network, he would probably say person, or scale, or locker room maybe. But if you were to look at this, you see quite a different story. You see a guy standing on a scale. You know how scales work, which requires some idea of physics. You know that he's looking at the scale. You know that he's trying to measure his own weight. You know that people tend to be self-conscious about their weight. You know that the person behind him is stepping on the scale and pushing down. Because of your knowledge of physics, you know that that's going to make the scale have a bigger number. Because of your knowledge of that guy's psychology, you'll know that that might make him feel embarrassed or uncomfortable because he thinks he ate too much. And then you also know who that person pushing down on the scale is, and because of your knowledge of who he is, it makes it maybe surprising that he's acting in this way. You can see the people behind him watching this scene and laughing, and to understand that, you need to know how it is that people look at each other. You understand that maybe they're surprised that this guy is doing this thing that's causing this guy to be embarrassed. So there's a lot going on in this image that we as visually intelligent humans could understand and perceive. And I think we're a long way away from building computer vision systems that can match that level of visual fidelity. But I'm hoping that as we move forward and continue to advance the field, maybe one day we'll get there. But in the meantime, I think that computer vision technology really has massive potential to improve all of our lives. It'll make our lives more fun through sort of new video game applications in VR, AR. It'll make our transportation safer with advances in autonomous vehicles. It'll lead to improvements in medical imaging and diagnosis. And overall, I think computer vision as a whole has a massive ability and potential to continue leading to massive improvements in all of our day-to-day lives. So that's why I think we should be studying computer vision. That's why I'm excited to be teaching this class this year. So that basically covers our brief history of computer vision and deep learning, except there's one little spot on the timeline that we didn't fill out, and that's this class. So with that, it's time to, if there's any questions about historical stuff, then we're going to move on to course logistics from here on out. No? Okay, great. So, course staff, who are we? I'm Justin Johnson. I'm a new assistant professor here in the Computer Science and Engineering Department. This is the first class I'm teaching here at Michigan. This is the first time I've been in this room, so I'm glad I found it and got the laptop connected. But I'm excited to be here, excited to be teaching you guys this semester. We have an amazing team of graduate student instructors that are going to be helping us out this semester. We have Yoon-Seok Jiang, who's here. Okay, that was a little awkward. We have Ki-Bak Lee. You don't have to stand in here. And we have Lo-Wei Zhao. So these guys are all experts in computer vision. They're all PhD students here. Yoon-Seok works in video understanding and generative models. Ki-Bak works in robustness and generalization. And Lo-Wei works a lot in vision plus language. So if you have questions about those particular research areas, you should go talk to them. So how to contact us. So this is an important slide, right? Taking pictures of this one's a good idea. Hopefully we can build some content systems that will extract useful information out from them automatically. But we have a course website that's up in this URL. The course website has all of the information that you'll need throughout the quarter. You can find the syllabus, the schedule. You'll find links to assignments there. You'll find links to lecture videos, assuming I set up the lecture capture properly. Really important, we're going to use Piazza for most communication with you guys. So we really encourage you, if you have questions about the course material, we're going to use Piazza as our main mechanism to communicate back and forth with you guys. So if you have questions about course content, questions about material, post those on Piazza. And similarly, when we need to make announcements back to the class to announce things like updated homeworks, about changes to logistics, we'll be announcing all of those through Piazza. So it's really important that you guys get signed up as quickly as possible. And one piece of note is that please don't post any code on public questions on Piazza. If you do need to ask particular questions about code, we ask that you make private questions that are visible only to the instructors. So we will have Canvas. I think I need to set that up still this week. But we're going to use Canvas primarily for just turning in assignments. Mostly we'll be using Piazza and the course website for this class. We will have office hours, both me and the GSIs, starting next week. And you'll be able to find the times and locations of the office hours on the Google Calendar that I set up here. Finally, we really want the vast majority of communication you do with us should be through Piazza. But if you have some kind of very sensitive topic that you would prefer to discuss directly with me, then you can email me directly. But for the vast majority of circumstances, you should be going through Piazza for course communication. That will ensure that everyone, all of the teaching staff is able to help you in a timely manner. And if you're able to if you're making public questions, it lets you all help each other and learn collectively and learn from each other's mistakes. So I think Piazza is a really great learning tool for that. So we're going to have an optional textbook. There's no required textbook for this class. On the schedule you'll find on the website, there will be recommended readings for all of the lectures. This textbook is totally optional. And it's completely available for free online, so you don't have to physically purchase a copy if you don't want to. So on course content and grading, the main bulk of the course is going to be 6 programming assignments. Uh-oh, is that a problem? Is that too many? Is that too many? All right, so we're going to have 6 programming assignments. That's going to be the bulk of the course. I think these are going to be really exciting assignments. We're going to use Python, PyTorch, and Google Colab. And we're going to walk you through the detailed implementations of a lot of the ideas that we talked about in lecture. We will have a midterm exam, and we will have a final exam. But there will not be any course project. The majority of the stuff you'll be learning is through the programming assignments. So we have a late policy. So don't turn it in late. But more seriously, you all get 3 free late days to use on your homework assignments. You don't have to tell us beforehand. Just turn it in late and we'll deduct them automatically. Once you've exhausted your late days, then we'll take 25% per day. I think something like that's pretty standard. Are there any questions about content, policies, late days, anything like that? Yeah, over here.
For the people that won't get off the wait list, will the course site, the lecture recordings, the assignments be freely available, or we have to log in to access that?
Yeah, so the question is, will the course materials be available for people not on the wait list? And they will be as freely available as I can possibly make them. So even if you can't get enrolled in the class, you can definitely feel free to follow along with the lecture slides, with the lecture videos, and with the course assignments. Yeah, question?
Yeah, for those late days, is that like one late day per one assignment, or did you blow all 3 late days on one assignment?
Yeah, it's up to you. You're all grown ups. You can use as many late days per assignment as you want. If you take too many, it'll be worth 0, so I don't recommend that. But the free late days, you can use as many as you want, and extra late days, you use as many as you want per assignment, but we'll just take off points as necessary. Yeah?
Are these group assignments or individual assignments?
So let's talk about collaboration policy. Right, so we really encourage you guys to work together in groups. I think it's great to discuss course material with your classmates and to learn together. But we have a couple of ground rules about that for collaboration policy. One is that everything you submit should be your own work. It's fine to talk about ideas with other students, that's great and encouraged, but you shouldn't be sharing or looking at each other's code necessarily. You can talk about things conceptually, but you shouldn't be turning in the same code as people you work with. Secondly, on the flip side, don't share your solution code with other people. This means don't post it on Piazza, don't give it to your roommate, don't put it on GitHub, because that will make it easier and more tempting for other people to violate collaboration policy in the future. And third, when you turn in assignments, we ask you to indicate who you work with when you turn in your assignment, and there will be more detailed instructions on that later. And in general, turning in something late or incomplete is much better than potentially violating collaboration policies, and not just in this course, but more generally. Any questions about that? Okay. So then, course philosophy. What are we here for, right? Our idea is that this class is not learn PyTorch in 90 days. This class is not learn deep learning in 10 lines of Python. You can find tutorials on the internet that tell you how to do that if that's what you want. But I think that learning about deep learning in that way does yourself a huge disservice. I think that you want to focus on fundamental concepts. We want you to understand not just the latest and greatest high-level APIs that wrap Keras and TensorFlow. We want you to understand the fundamentals of how those APIs might have been implemented, why they were implemented the way that they were, such that when faced with the next piece, the next bit of technological tools, you understand the fundamentals and can do them yourself. What that means is that you'll be writing a lot of backdrop code yourself in this course. I think that it's very important for people to learn how to compute gradients and how the computation of gradients affects the overall flow of learning throughout your system. So for the first several assignments, you'll be using no autograph, you'll be using no TensorFlow, you'll be deriving and implementing your own backprop, your own gradient computations, and you will be a better computer scientist for it. So given that, we prefer you to write, for the purpose of pedagogy, we're going to encourage you to write things from scratch, rather than relying on existing open source implementations. Again, this will make you a better deep learning practitioner. That said, we're also practical. We're going to give you lots of tools and techniques for debugging and training big neural networks, because it's tricky when you can't rely on that 10 lines of code wrapping around lots of stuff. So we're going to talk a lot about how you can practically get these things to work. What tips and tricks should you be using when developing and debugging and training neural networks? We will use state-of-the-art software tools like PyTorch and TensorFlow, but only after you've earned your wings by writing a lot of backprop code yourself. We're going to focus on state-of-the-art. A lot of the material that we cover in this course, despite the long historical context that we talked about in this lecture, the majority of the actual concrete implementations and concrete results we've discovered that we'll talk about in this course have been discovered in the last 5 to 10 years. So this has a couple interesting implications for teaching a course. That means that there aren't good textbooks for this stuff. That means that there might not be great resources outside of original research papers for learning about this stuff. So that's going to be maybe a bit of a struggle and a bit challenging. But on the upside, I think it's really exciting to be learning about such state-of-the-art material in a classroom setting. So So then, in terms of, so also in philosophy, we would also have a little bit of fun. So we'll be covering some sort of fun topics, like image captioning that we got a good laugh when I put it up here a couple slides ago, and some of these deep dream and artistic style transfer that lets you use neural networks to generate cool pieces of art, not just improving our lives. So in terms of the course structure, generally the first half of the course will focus on fundamentals. We'll talk about the details of how to implement different types of neural networks. We'll cover fully connected, convolutional, recurrent neural networks. We'll talk about how to debug them, how to implement them, how to train them, and we'll be very detailed. And by the end of this module, you'll basically implement your own convolutional neural network system from scratch. Now, in the second half of the course, we're going to shift a little bit in flavor. And here, we're going to focus more on applications and more emerging sort of researchy topics. So around that point in the course, you'll notice a bit of shift in tone in the lectures. So they will become a little bit less detailed. We'll sometimes skip over some of the low-level details and perhaps refer to papers if you need to know those details. And instead, the lectures will more focus on giving you an overview of how these different things are used across different applications in computer vision and beyond. In the second half, we'll talk about things like object detection, image segmentation, 3D vision, videos. We'll talk about attention, transformers, vision and language, generative models. I think it's going to be a lot of fun. But because there's a lot to get through, first homework assignment will be out over the weekend. That will cover basically an intro and a warm-up to the Colab and PyTorch environment that we'll be using throughout the quarter. So this is not intended to be a difficult or a long assignment. This should be out over the weekend, and whenever we get it out, it'll be due a week after that. And everything you need to do this first homework assignment we'll get through in Monday's lecture. So with that said, welcome to the class, and come back on Monday when we'll talk about image classification, start diving into the course material.